Okay, so let us continue with our solution, which we did not finish in the previous video. So we have in fact gone through the definition of a finite product of real numbers, and we have also stated the basic results of finite products which correspond to similar results of finite involving finite series. So now we need to define products over finite sets, just like we had sums over finite sets. So that is the next thing. So it's a continuation of the previous solution. I mean the solution which in fact is going on still. Let X be a finite set having n elements, and let f be a real valued function on X. Let this be a function. We define the product of these functional values f of x as x varies over x as follows. We first choose a bijection G from this set of natural numbers to X. Now we already know that such a bijection exists by definition because X has n elements, and in fact that's what we mean when we say X has n elements. We then define this product so at least now what we are writing or what we will write, you already know what we will write and what we are doing here, because you have the experience of going through similar things involving sums. Okay, so we have defined this product in terms of a finite product of real numbers. And you can now imagine that just like we had to prove that this definition is well defined, which more specifically demands that the definition does not depend on our choice of G. We had to prove this when we defined this kind of sums. A similar result is there for products, which however we are neither going to state nor going to prove, because it is exactly similar to the result which proves that sums over finite sets are well defined, and that means they do not depend on the specific choice of this G. It does not matter what G one uses, because you know that X having n elements means there is at least one bijection between these two sets, but there may be more, and one person say chooses G, another person may very well choose a different bijection, but we have already proved that the that choice does not in fact affect this final value of this sum. It does not affect this finite series value. Here also it will not affect. So there is a result. Now simply because here I am going to mention that there is a result which will prove that this product is well defined does not mean that you also just keep it like that. In fact, I strongly urge you to state that result and prove it just for yourself. So we write like this: to make this definition well defined, there is a result just like what was the corresponding result for sums, proposition 718. We omit the statement as well as the proof of this result. So we assume that we have in fact already stated that result, we have proved it, and because of that this kind of products are well defined. Now we move forward with that assumption. So now we are going to state the basic properties of this type of products, which will correspond to similar properties for sums. And if you remember, while stating the properties of finite products of real numbers, we called that result 1. So here we are going to name this one result 2. We now state a result for products over finite sets corresponding to that result, which gives us basic properties of sums over finite sets. Corresponding to proposition 7.1.11. So this is our result 2. So just like all the things we have already gone through, this also has those parts. If part A is this: if the set X is empty, and if f from X into the set of real numbers is a function, just like before. i.e. f is the empty function, that is the only function which can have the empty set as its domain. Then the product of f of x as x varies over x is 1, not 0. In case of sums, we had 0 because the definition of a finite series gives us 0 if the you can understand what I am trying to say here, that the 0 that we have in case of sums actually comes from the definition. Here also we are having 1 because the definition of products is like that. So here in part A we have the empty set, in part B we will have any singleton set having precisely one element. If the set X consists of a single element, that is X looks like this, x0 is the sole element in X where x0 is any object, and if f from X to R is a function, then this product equals f of x0. This is just like what we have in case of a sum. Part C, it does not really matter which one we call part C and which one we call part B or anything. We just have to cover all the parts. Let X be a finite set f from, now we are not saying anything about the cardinality of X, only we are saying that it is a finite set. So that means the cardinality of X is a natural number. It's no longer necessarily 0 or 1, it may be any natural number, and f is a real valued function defined on X, is a function, and g from y to x is a bijection, is a one-to-one onto function, where y of course is also a set and y has the same cardinality as x. That is because there is a bijection between them and X is finite. In simple terms, Y is finite and has the same number of elements as X. We have started with let, okay, then this product is equal to another such product f of g of y, where y varies over y. So here also it's just like that corresponding result for sums, only difference is that we have product here and there we have sum. Then part D is that one. Okay, let n and m be integers which are related like this, be integers, and let x be the set defined like this. It's the set of all integers I which satisfy these inequalities. Let AI be a real number for every I, or we can write in more detail, for every integer I satisfying this. Then this finite product where I varies from n to m is equal to this product where I varies over the set x. This is also just like the similar result for sums. Next, we are not going to prove this result too. We will just complete writing its statement down, and then that's it. That will be the end of the solution. But again, I urge you to go through the proof. At least convince yourself that the proofs of these parts are exactly like the proofs of those corresponding parts involving sums. E. In part E we have what? Okay, this one. Let x comma y be two disjoint finite sets. Both of them are finite sets and they are disjoint. There is no element in common, or in other words, their intersection is empty. Note that we are not saying anything like they have the same number of elements, nothing like that. Only thing is that they are both finite and they are disjoint. And let f be a real valued function defined on their union. Then the product of these terms as z or z, whatever you want to call it, varies over x union y is equal to this product times this product g of okay, there is only one function. What am I writing? Y belonging to y. in the corresponding result for sums, we had sums, and here in place of this intermediate multiplication we had addition. Then part F. Here we have one function and two sets. In part F we have two functions and one set. Let X be a finite set and let f from x to r and g from x to r be functions. Then the product of terms like this, f of x, g of x, is equal to the product of f of x as x varies over x times the product of g of x as x varies over x. Okay, these two equations, structurally they look similar from a distance if you don't look too deep into them, but they of course are different, you can see that. Then f, we have written f, okay, then g. Let x be a finite set f from x to r be a function and c be a real number. Then this product where the things which we are taking product of, those things look like this, c times f of x, where c of course is not changing but f of x is changing because x is changing. That is equal to here, however, just simply c will not come out since we have that many c's, as many elements we have in x. So that means in place of just simply c, we have to write this power of x, where the exponent is the cardinality of x, because that means these will appear. So you take their product and you get this power. This notation, recall, it denotes the cardinality of x, or more simply it is just the number of elements the set x has. Different mathematicians use different notations for this same thing. Some would write this like this, the size of x. Herstein in topics in algebra would write like this, order of x, all of them in the same thing. In this text, the professor Tau uses this using hash, number of elements in x. Next, H. H is that comparison one. Let X be a finite set and let here also two functions are there, f from x to r and g from x to r the two functions such that this for all x belonging to x. So f and g are real valued functions on x and they are related like that. Some inequalities are there and they are non-negative. They never take any negative real number as their value. Then the product of the functional values f of x as x varies over x is less than or equal to the product of the functional values g of x as x varies over x. And finally we have one more which involves absolute value. Let x be a finite set and this be a function. Then the absolute value of this product is equal to the product of the absolute values. So that's just it. We are going to write the solution till this only. But once again I am repeating this again. Please at least think about the proofs. So we move on to the next exercise. This is the fourth one, I think, if I am remembering correctly. Yes. In this one, we want to prove the binomial formula or the binomial theorem, which states the binomial formula. But why suddenly binomial formula? That is because that's the result which we actually already know, but since in this text we have decided to prove everything, so why not that one also? And the reason for the binomial theorem or formula being in this section is simply the fact that its statement involves a finite series. That's just it. So we first state it, define the factorial function in factorial for natural numbers, and these things are hardly anything new to any one of you. In fact, you already know what these things are, but again, just let's go through them once more. There is another notation for writing n factorial like this, but it's old notation. We no longer use this. We use this notation n followed by the exclamation mark. By the recursive by the following recursive definition. First, we define 0 factorial, which by definition is 1, and we define n plus 1 factorial recursively to be n factorial multiplied by n plus 1 for all natural numbers n. Now the actual statement of the binomial formula for x and y. For any real numbers that I needed to write. For any real numbers x and y, prove that. Here also we can write, okay, there will be space, x plus y whole to the power n is equal to summation n factorial divided by j factorial times n minus j factorial multiplied by x to the power j times y to the power n minus j. So it's a finite series where j varies from 0 to n, but we need to of course also mention what n is. N is any natural number. For all natural numbers n, and there is a hint also, which is the, you already know, induct on n, the most generic hint that one can give in this situation. Okay, so let's just see the solution. We are going to now prove this formula by induction on n. So our base case will be when n is 0. So we need to first make sure that the formula is true when n is 0. Note that x plus y whole to the power 0 by the definition of real exponentiation is equal to 1. Now if you look carefully, 1, this real number 1 can be written like this. 0 factorial divided by 0 factorial times 0 minus 0 factorial times x to the power 0 times y to the power 0 minus 0. At first glance, it seems like there is something wrong with this denominator because zeros are appearing, but because 0 factorial has been defined to be 1, which is non-zero, there is no problem. And in fact, using this recursive definition, you can prove many things about the factorial function. One of them being the fact that the factorial of any natural number is a positive natural number, that is a positive integer, even when the natural number itself is not positive. 0 factorial is also 1, and the others of course will be larger and larger. And in fact, as n increases, n factorial increases at an extremely rapid rate. 0 factorial is 1, 1 factorial is also 1, which is in fact no change at all. But then 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 124. So like that, the jump is too much. Okay, so we have written one like this. Now, using elementary properties of finite series, note that this thing actually equals this finite series value. 0 factorial divided by j factorial times 0 minus j factorial multiplied by x to the power j times y to the power 0 minus j, where j varies from 0 to 0. Since in this finite series the lower limit for the index and its upper limit, they are the same, so you know that the finite series will have the value which you can obtain by putting just j equal to 0 here, and that's what you have here. Now look at the first term and the last term in this series of equations. This of course is the left hand side when n is 0, and this is the right hand side when n is 0. We have n here, we have 0 here. Here you have n, here you have 0. N minus j, 0 minus j. J of course is there, and here in place of n you have 0. So the formula is true when n is equal to 0. This is our basis for induction. This will get the induction started. Now next, assume that the formula is true for some natural number n. Is true for some natural number n. Okay, now we are going to go through a series of steps where we will start with this. We need to prove that this equals such a series where I wrap that off. You have n plus 1 in place of n. So let's see what we can do. By one of the rules of exponents, or in fact by the very definition of exponent, I mean real exponentiation, this equals this. Now in the next step, our induction hypothesis that the formula is true for n, some n, allows us to write that finite series in place of this one, this nth power of x plus y. That is, we have this, okay, I have to write carefully, I don't have much space. N minus j factorial times x to the power j times y to the power n minus j, where j varies from 0 to n. Now using distributive law and everything, or just doing your usual elementary algebra, what you do, you first multiply all the terms of this finite series by x, and then plus all the terms of this finite series again by y. So you get a sum of two finite series. One of them is this. Multiplying by x, we get this. Plus another such where all the terms we multiply by y. So y to the power n plus 1 minus j, and j of course again here also varies from 0 to n. I hope all these things are visible. Here in this series, j has the lower limit 0 and upper limit n, just like the first one. But then what? In carrying out this entire calculation, we are every now and then going to use basic properties of finite series, which we in fact have already proved in the text itself. One such property will now allow us to write the first finite series like this. Summation, everything here remains the same, n minus j factorial times n minus j factorial times x to the power j times y to the power n minus j. The lower limit is also the same, but in place of upper limit, what we do, we write n minus 1. So that means we have written, loosely speaking, one term less in this sum or series, and that one term is this expression when you put j equal to n. Now let's just see what we will get if we put j equal to n here. N factorial divided by j factorial will become n factorial, and n minus n factorial x to the power, oh, I think I have already made a mistake. We have j here, that is fine, but here we don't have j because I am writing the first sum now. So it is j plus 1. This type of mistakes are unavoidable, but you should also be able to notice them quite quickly and rectify them. And what will we have here? If you put n in place of j, you have x to the power n plus 1 and y to the power n minus n. This will of course be 1 and it will vanish. What about this thing? N factorial and n factorial cancel out. There is no problem with that provided n factorial is not 0. It is never 0. We have already said that. So these two things cancel out, and here in the denominator you have 0 factorial, which becomes 1. So that means this part within this round brackets entirely becomes 1. This becomes 1. So we are left with only x to the power n plus 1. So that means plus x to the power n plus 1. Now in the second series what we do, we will write the series, but we will not start with 0. That means here we will change the lower limit. We will write 1 in place of 0. That means we are losing the term which corresponds to j equal to 0. That one we will write first, and then followed by this series which has one term less than the original series. So plus this thing when j is equal to 0. Now if j is 0, first of all 0 factorial we get here in the denominator, which becomes 1 and it vanishes. If you put j equal to 0 here, you get n factorial divided by n factorial. So they cancel out, and here also this thing, this coefficient becomes 1, it vanishes. If you put j equal to 0 here, this power of x vanishes. Putting j equal to 0 here, you get the power of y to the power n plus 1. So that means y to the power n plus 1, which is just this thing when j equal to 0, plus this finite series where j varies from 1 to n. Okay, so we have taken out one term from each series. From this series, loosely speaking, we have taken the last term out, and from this second series we have taken the first term out. That last term is x to the power n plus 1, here the first term is x to the power, y to the power n plus 1. Okay, now what we do, we are going to use one of the properties of finite series and tweak this second series slightly. You will see how. Let us first of all write x to the power n plus 1 plus y to the power n plus 1 plus the first set y half space here. I think it's better to first write the series. N factorial divided by this times x to the power j plus 1 times y to the power n minus j, where j varies from 0 to n minus 1, plus we will write this y to the power n plus 1 last, but before that let us change this series, the appearance of this series slightly. You recall that you can do something like this. You can subtract an integer from both the lower limit and the upper limit, but when you do that, you have to add that integer here to that index. That means what I am trying to say is that now in place of this series we are going to write an equivalent one. Both of them will have the same value. Instead of 1, we are going to put 0 here. That means I have subtracted 1 from the lower limit. So I also have to subtract 1 from the upper limit. So in place of n, I have n minus 1. To compensate for this change, here we will have j plus 1 in place of just j. Here we have subtracted 1, here we have to add 1. And this, if you go back to the basic properties of finite series, you will find there is a property which allows this to happen, where the adding or subtracting that integer, in place of that integer we have k. Now note carefully that if I write j plus 1 in place of j, because there is a minus sign, so I will have n minus j minus 1. I am writing this series. I was on the brink of making mistake because I am changing this series and I am looking at this. No, that's not it. See, these things quickly get so confusing. I am changing this series. In fact, this is the second series after I have taken out y to the power n plus 1. So I got confused between this one and this one. So there was a confusion also about what are the things that I was confusing. So that means we have 0 here, we have n minus 1 here. Now I will write j plus 1, because I have to add plus 1. Now here if I write j plus 1 in place of j, 1 and minus 1 will cancel out and I will have y to the power n minus j plus finally y to the power n plus 1. I hope I have not messed up in this confusion. Okay. Now you will see why in fact we changed that series. What is the purpose for that? Note that in these two series, that's why we have written them like this, one next to the other. In fact, we can also put them within square brackets to emphasize the fact that we are looking at their sums here. The index j has the same lower limit and the same upper limit. Also, one more thing has happened. These are same, x to the power j plus 1, y to the power n minus j. So using another elementary property of a finite series, the sum of these two series will be a single series which will look like this, plus I cannot possibly write those xy terms here, so instead let me just write like this, times x to the power j plus 1 times y to the power n minus j, where j varies from 0 to n minus 1 plus y to the power n plus 1, because actually a series where we have where the things that we are taking the sum of this plus this, but there you have this common terms, so you can take that common out and have this thing. Now plus if one calculates, one will find that this thing inside square brackets equals this. That is, one can show that this expression, this sum, equals this. X to the power j plus 1, y to the power n minus j. Oh, it has ultimately come out like this. Do I have anything here that I may have written in its place? What we have done here is not wrong, but because of the way we have done it, we have to again go through one more step. Without further complicating matters, let's just continue with what we have. Instead of changing this second series to this, things would have been nicer if we changed this series instead. But anyway, we can make that change now. So far there is no problem. We have now finally got this. Now we proceed further. Plus. Now we we write a similar change here now. So there we subtracted 1 from the lower and upper limit of a finite series. Now we are going to do the opposite thing. We are going to add 1 to the lower and upper limit, because we can in fact add any integer k. So we can essentially subtract or add, anything we can do. So now what we are going to do, now our series will change to a series where the lower limit will be 1, upper limit will be n, and here we have to subtract 1 from j to compensate for that. So one to n, and in place of j, simply putting in place of j, we are now going to write j minus 1. J minus 1 factorial. Okay, what will happen here if I write j minus 1? Have I written this thing correctly? That also is another question. If I use the standard notation for these symbols in oh yeah, there is a mistake here also. There is nothing wrong in the numerator, but in the denominator we will have this. Minus j plus 1 factorial. Okay. Note that we are not using these notations in this exercise. That is because we don't need, these are, you already know, they are called binomial coefficients, and there is another notation for say for example writing this. People also write like this, NCJ, n choose j. It gives you the number of combinations of n objects taking j at a time. But we don't need such notions, so we don't bother to, the author has not bothered to devise a separate notation for the binomial coefficients. That is why in fact I went through these things, these confusions. Okay, so now if I write, so we are adding 1 to the limits, so we are subtracting 1 from j. That is, in place of j, we are now going to write j minus 1, or the same thing, in place of j plus 1, we are writing j. So we don't have j minus 1 here. We have just j here, j factorial. Here we will have n plus 1 minus j factorial. Here we have x to the power j, and what about this? If I am subtracting 1 from j, because I have minus j here, that is the same thing as adding 1 to minus j. That means y to the power n plus 1 minus j plus y to the power n plus 1. Again, using elementary properties of finite series, if we write like this, and now our limits are, both of them are different. The lower one is 0 and the upper one is n plus 1. Now what happens if you take j equal to 0 here? 0 factorial vanishes. Here you have 0, so n plus 1 factorial, they also cancel out. So this term becomes 1. If you take j equal to 0, the x power does not, it vanishes. Taking j equal to 0 here gives you y equal to, y to the power n plus 1. So that term is this. And what happens when you take j equal to n plus 1? Again, if you do the calculation here, n plus 1 factorial, they cancel out, and in the denominator you have 0 factorial. So that also becomes 1. So this thing vanishes. Here you have n plus 1, so x to the power n plus 1, and this term vanishes because it becomes y to the power 0. So writing different limits actually includes this terms inside the series, and besides 0 and n plus 1, the other values of j are of course here, the intermediate values. So now you see what we have finally got. Is it not the right hand side when you have n plus 1 in place of n? It is, because you see the upper limit is n plus 1. Here you have n plus 1, here also you have n plus 1. Previously you had n minus j factorial. Here previously you had n, now you have n plus 1. So this tells us that the formula is also true for n plus 1. Hence, the formula is true for n plus 1. Okay, now the confusion that we were having is we wrote this incorrectly, no? So you may be a little doubtful. You just try to, or in fact let me just quickly show that in fact we will have this, we will actually have this. What happens if you manipulate this sign? There are many things that can be taken common out. First of all, you have n factorial common. You can take j factorial common out from this one and this one, because this one by definition is j plus 1 times j factorial. Okay. What else? N minus j factorial you can take common out, because this one is n plus 1 minus j times n minus j factorial. So what survive in the first term? We have, oh, have we managed to take everything common? How is that possible? J factorial. Okay, let's see what we get, or whether we again run into something wrong. N plus 1 minus j. J factorial times n minus j factorial. Now this one will be what? J plus 1 n plus 1 minus j. Yeah, I think we have, okay, what the hell? It is in fact wrong. So something must have gone terribly wrong in our calculation. Now there are two ways of circumventing this peculiar situation. One is to redo the calculation, and one is to just leave it unfinished like this and go to the next exercise, which in fact is the last exercise in this set of exercises. I think it's better to redo the calculation. What do you say? So that we don't leave anything unfinished. If time permits, we will quickly go through the second exercise. If not, we have to again continue next Sunday. All of these things are happening because I did something which took me off course, and then I tried to come back, but in this process I messed up very badly. Okay, so now we will carefully redo the calculation, because we have in fact seen what I was trying to do once. Now I don't need to explain that much. There is no problem with this part, but now comes the problem. So first we take the that term outside, which corresponds to j equal to n, and that term is x to the power n, j equal to 0 to n minus 1 From here we take that term outside, which corresponds to j equal to 0, and that is y to the power n plus 1. X to the power j, y to the power n plus 1 minus j. No more mistakes. J equal to 1 to n, j n minus j, j n minus j, j c j plus 1 n minus j, j n plus 1 minus j. Okay, yes. Okay, then what? Which one of these theories in fact I have changed? That is the thing now. J equal to 1 to n. So in our previous calculation we changed this series, now we change this series. In fact, that is what we had to do. Okay. And what is the change? Here the change is adding 1 to the limits. Let us do that first. 1 n, it was n plus 1, now it becomes n, and subtracting 1 from the j's, n factorial j minus 1 factorial. Here if we subtract 1 we get n plus 1 minus j factorial. Here if you subtract 1, j minus 1 plus 1 becomes j, and this one is y to the power n plus 1 minus j. That is simply we are writing j minus 1 in place of j, plus x to the power n plus 1 plus y to the power n plus 1 plus this other thing. N plus 1 minus j. N plus 1 minus j. Okay. Now I can write the sum of these two series. Here I have forgotten to write the limits. Now again the limits are same, 1 to n, and here also x to the power j, x to the power j, y to the power n plus 1 minus j, y to the power n plus 1 minus j. So I can write just like before, j equal to 1 to n factorial divided by j minus 1 factorial times n plus 1 minus j factorial plus this one, n factorial divided by j factorial times n minus j factorial times x to the power j times y to the power n plus 1 minus j plus y to the power n plus 1. So that becomes what? Plus summation n plus 1 factorial divided by j factorial times n plus 1 minus j factorial times now we make j vary from 0 to n plus 1. When j is 0, this becomes 1, we have already seen that, and we have y to the power n plus 1. When j is n plus 1, again this becomes 1, and we get x to the power n plus 1. So those two things outside these two terms have now been included in this slightly larger finite series. Now your question of course would be this, whether now this actually becomes equal to this. Let us see. First of all, just like before, we can take n factorial common out. We can take j minus 1 factorial common out from these two things, because j factorial is j times j minus 1 factorial. And from this and this we can take n minus j factorial common out, because this is n plus 1 minus j times this n minus j factorial. So here we are left with and here we are left with 1 over j. We can take these things back to where they came from. We can multiply j minus 1 factorial with j. That will give us again j factorial in the denominator. Just like that, multiplying this thing and this thing gives us n plus 1 minus j factorial. Now here j and minus j cancel out, and we have n factorial times n plus 1, so that is n plus 1 factorial. So we indeed get this. And now the calculation is okay. You may of course have, you may be wondering, why don't I edit these videos and edit these mess ups out? That is because I don't really like editing something out. You get to see what really happens when we go through these things, how we mess up with things, then how we recover. All such things should actually be there. It should not be like you are just showing something and everything is going okay all the time. In fact, that is never the case. In most of the cases, we mess up and then we redo everything and make things okay. So you need to see the process also. So instead of rushing through the next exercise in a somewhat hasty manner, let's just continue. Let's just postpone that and let's continue from the next part. We will, in the next part, we will first of all, of course, solve this exercise, complete this set of exercises, and then we will start the theory of infinite series. So that's just it for tonight. If you want to say something, if you want to write some comments, you are welcome to do that. Or you can mail me also at my address, usual mail address, which will be there in the description. You will find the link there. And this coming, tomorrow we don't have any upload. This coming Tuesday we will do what? We have already gone through group theory, graph theory, field theory. So let's do vector spaces. Okay, so that being said, so see you next Tuesday. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.